Hello, I'm Sarah, and I'm excited to guide you through Unlock the Secrets of the Jacobi Symbol, Math that Cracks Codes. Jacobi symbol for various k along top and n along left side. Only are shown, since due to Rule 2. Below any other k can be reduced modulo, n quadratic residues are highlighted in yellow. Note that no entry with a Jacobi symbol of -1 is a quadratic residue. And if k is a quadratic residue modulo a coprime n then, but not all entries with a Jacobi symbol of 1, see the in rows, are quadratic residues. Notice also that when either n or k is a square, all values are non-negative. The Jacobi symbol is a generalization of the Legendre symbol. Introduced by Jacobi in 1837, it is of theoretical interest in modular arithmetic and other branches of number theory, but its main use is in computational number theory, especially primality testing and integer factorization. These, in turn, are important in cryptography. Dive into the fundamental concepts that underpin this fascinating mathematical tool. For any integer, a, and any positive odd integer n, the Jacobi symbol is defined as the product of the Legendre symbols corresponding to the prime factors of n. $left frac n right equals left frac p1 right, alpha 1 left frac p2 right, alpha 2 c dots left frac pk right, alpha k $where n equals p1 alpha 1 p2 alpha 2 pk alpha k is the prime factorization of n. The Legendre symbol is defined for all integers, a and all odd primes p by $left frac p right equals left beginner arl 0 and textif a equiv 0 p mod p 1 and textif a not equiv 0 p mod p text, and for some integer x colon a equiv x2 p mod p minus 1 and textif a not equiv 0 p mod p text, and there is no such x. End array right $. Following the normal convention for the empty product equal 1. When the lower argument is an odd prime, the Jacobi symbol is equal to the Legendre symbol. Delve into the fundamental values that underpin this fascinating mathematical concept. The following is a table of values of Jacobi symbol with n less or equal to 59, a less or equal to 30, n odd. Delve into the fundamental properties that make the Jacobi symbol so powerful. The following facts, even the reciprocity laws, are straightforward deductions from the definition of the Jacobi symbol and the corresponding properties of the Legendre symbol. The Jacobi symbol is defined only when the upper argument, numerator, is an integer and the lower argument, denominator, is a positive odd integer. 1. If n is an odd prime, then the Jacobi symbol is equal to, and written the same as the corresponding Legendre symbol. 2. If then $left frac n right equals left frac bn right equals left frac a pm mc dot nn right $. 3. $left frac n right equal begin cases 0 and textif gcd a n ni 1 pmon and textif gcd a n equal 1. N cases $. If either the top or bottom argument is fixed, the Jacobi symbol is a completely multiplicative function in the remaining argument. 4. $left frac ab n right equals left frac a n right left frac b n right quad text so left frac a 2 n right equals left frac a n right 2 equal 1 text or 0. $. 5. $left frac a m n right equals left frac a m right left frac a n right quad text so left frac a n 2 right equals left frac a n right 2 equal 1 text or 0. $. The law of quadratic reciprocity. If meters and n are odd positive coprime integers, then 6. $left frac mn right left frac nm right equal -1 t frac m -1 2 c dot t frac n -1 2 equal begin cases 1 and textif n equiv 1 p mod 4 text, or m equiv 1 p mod 4 -1 and textif n equiv m equiv 3 p mod 4 n cases $. And its supplements. 7. $left frac -1 n right equal -1 t frac n -1 2 equal begin cases 1 and textif n equiv 1 p mod 4 -1 and textif n equiv 3 p mod 4 end cases $. And $left frac 1 n right equals left frac n 1 right equal $1. 8. $left frac 2 n right equal -1 t frac n 2 -1 8 equal begin cases 1 and textif n equiv 17 p mod 8 -1 and textif n equiv 35 p mod 8. N cases $. Combining properties 4 and 8 gives 9. $left frac 2 amps n right equals left frac 2 n right left frac a n right equal begin cases left frac n right, and textif n equiv 17 p mod 8, left frac n right, and textif n equiv 35 p mod 8. N cases $. Like the Legendre symbol, if equals -1 then A is a quadratic non-residue modulo n, if A is a quadratic residue modulo n and GCD. A n equals 1, then equals 1. But unlike the Legendre symbol, if equals 1 then A may or may not be a quadratic residue modulo n. This is because for it to be a quadratic residue modulo n, it has to be a quadratic residue modulo every prime factor of n. However, the Jacobi symbol equals 1 if, for example, A is a non-residue modulo exactly 2 of the prime factors of n. Although the Jacobi symbol cannot be uniformly interpreted in terms of squares and non-squares, it can be uniformly interpreted as the sign of a permutation by Zolotayev's lemma. The Jacobi symbol is a Dirichlet character to the modulus n. Delve into the mechanics of how to actually compute these fascinating symbols. The above formulas lead to an efficient algorithm for calculating the Jacobi symbol, analogous to the Euclidean algorithm for finding the GCD of two numbers. This should not be surprising in light of Rule 2. 1. Reduce the numerator modulo the denominator using Rule 2. 2. Extract any even numerator using Rule 9. 3. If the numerator is 1, Rules 3 and 4 give a result of 1. If the numerator and denominator are not coprime, Rule 3 gives a result of 0. 4. Otherwise, the numerator and denominator are now odd positive coprime integers, so we can flip the symbol using Rule 6, then return to Step 1. In addition to the codes below, Riesel has it in Pascal. Delve into the practical application of these concepts, and we'll now explore implementation in Lua. Function Jacobi n. K assert, k0 and k%2 equals 1. N equal n% kt equal 1, while n equals 0 do, while n%2 equals 0 do n equal n/2 r equal k%8. If r equals 3 or r equals 5, then t equal t and n. K equal k. N if n%4 equals 3, and k%4 equals 3, then t equal t end, n equal n% k end. If k equals 1, then return t else return 0 and end. Delve into the practical application of this fascinating mathematical tool implementation in C++. //n is represented as a n int Jacobi, int a int n, assert n0, and an n%2 equals 1. /step 1 if a percent equals n0 a plus equals n. /handle a 0 /step 3 int t equals 0. /XOR of bits 1 and 2 determines sign of return value, while a /step 2, while a %4 equals 0, a slash equals 4. If a %2 equals 0, t equals n, // could be equals n and 6. We only care about bits 1 and 2 amps / equals 2, // step 4 t equals a and n and 2. / flip sign if a %4 equals n%4 equals 3 int r equal n%, a n equal r. If n equals 1, return 0. Else if t1 and 2 return -1, else return 1. There is another way the Jacobi and Legendre symbols differ. If the Euler's criterion formula is used modulo a composite number, the result may or may not be the value of the Jacobi symbol, and in fact, may not even be -1 or 1. For example, $begin-a-line left frac 1945 right, and equals 1 and in text, and in 19 frac 45-12, and equiv 1 p mod 45. Left frac 821 right and equals -1 and in text, but in 8 frac 21-12 and equiv 1 p mod 21. Left frac 521 right and equals 1 and in text, but in 5 frac 21-12 and equiv 16 p mod 21. End-a-line $. So if it is unknown whether a number n is prime or composite, we can pick a random number a, calculate the Jacobi symbol, and compare it with Euler's formula. If they differ modulo n, then n is composite. If they have the same residue modulo n for many different values of a, then n is probably prime. This is the basis for the probabilistic Solovay-Strassen primality test and refinements such as the Bailey-PSW primality test and the Miller-Rabin primality test. As an indirect use, it is possible to use it as an error detection routine during the execution of the Lucas-Lehmer primality test, which, even on modern computer hardware, can take weeks to complete when processing Mersenne numbers over $begin 2. 136,279,841. 1 $, the largest known Mersenne prime as of October 2024. In nominal cases, the Jacobi symbol, $begin left, fracas I2MP right, and equals -1 and I ni 0 $. This also holds for the final residue $begin s. P-2, $, and hence, can be used as a verification of probable validity. However, if an error occurs in the hardware, there is a 50% chance that the result will become 0 or 1 instead, and won't change with subsequent terms of $begin s $, unless another error occurs and changes it back to -1. The Jacobi symbol offers a surprisingly powerful method for determining primality and securing communications.